So what I'm going to talk about today is maybe a broad overview of the research that my group's doing in areas that I'm hoping to engage with the folks doing robotics at Penn. And there's two broad chunks to my research. The main piece is this construction of digital twins for what we call systems of systems. So you can just imagine models that have different parts. It might be different kinds of physics, different domains, different anything where you have modules that have to be coupled together. And the idea, digital twins is a bit of a buzzword. What I mean when I say digital twins is a computer model, that would be the digital twin that can make predictions about a physical system. Right, so over here, that would be this arrow. With the assumption, finite elements can do that, but there's the added aspect that we want to do this in real time. And then also, we have this closed loop component. So we also want to be able to take data in real time that's coming off of the system and use that to update our physical model. So all of this, the core of it is that machine learning lets us make these kind of predictions 1,000 times plus faster than traditional PDE-based solvers. The big difference here is that how can we, compared to other people doing ML for this, how can we get the same kind of guarantees that you need, like numerical stability, physical realizability, uncertainty quantification, right? Not just like chuck it into a big black box PyTorch thing and see what comes out the other side. So the vision for this DOE center that Mark mentioned is that, one, we can construct these kind of real-time models, but then once we have them, we can use them to do distributed sensing across the Earth. So the Earth system model consists of many submodels like atmosphere, ocean, sea ice, land ice, Earth, and so on. And they're all coupled together. They're these ancient Fortran codes, right? But many physical systems, they straddle both of those. For example, you could have a wildfire in the Earth model that triggers a hurricane very far away, right? So in Earth science, we call that telecasting. And what we're envisioning is that we can develop distributed sensor networks, probably on some sort of autonomous vehicles that can go out and sense these events in real time. We want to integrate that into these models. The bread and butter in my group, we do a lot of data-driven modeling and machine learning augmented forward simulation. So here's a sample of some of the projects that we're working on right now. We're looking at upscaling shock physics and fusion processes in both magnetic confinement fusion and inertial confinement fusion reactors. So this is an example where there's a lot of physics you have to get exactly right, like the conserved fluxes, conservation structure leads to the correct propagation of shock speed. There's gauge symmetries in electromagnetism. There's all these things that go beyond the sort of rotational invariance and translational invariance that people, when people say structure preservation and machine learning, that's usually what they mean in computer vision. But we have these much finer grained and more challenging symmetries that we have to figure out how to preserve. We're also looking at how do you integrate multimodal data. So traditionally multimodal would mean text, images, audio, whatever. In a scientific setting, that could be many different kinds of material characterization that might not be amenable to first principle physics modeling. And so how do we assimilate that information alongside a traditional PDE-based model? And so we're very interested in this for hypersonics. When you have a reentry vehicle and masses ablating off, right, you can get spectral signatures and those kind of things. So imagine a constitutive law for material that actually takes spectroscopy data as an input. Another picture is bridging scales between materials and engineering scale. So for lithium-ion batteries, I'll talk a bit more about this later. A lot of the uncertainty in the material translates to the failure that happens when, for example, you have thermal runaway, and a battery rack will, catch on fire and explode. Right? So if you really want to do uncertainty quantification and understand these extreme scenarios, you need to be able to understand how uncertainty propagates up from a material all the way up to the material, or up to the HVAC system that you're trying to design. Okay, so the second goal of my group when I was at Sandia, I ran a relatively large group that was looking to use autonomous or semi-autonomous experiments to do materials discovery. So that means both the fabrication of materials. We were mostly interested in electroplating, physical vapor deposition, these kind of processes that make thin films. So both looking at how we can do high throughput fabrication and characterization And then on the machine learning side, the question is, what can you do with all of this data that comes off of this, both in process and post-process kind of characterization? So again, this is a picture where multimodal machine learning, which has been it's a huge thing right now, right? For example, like I could turn on here. Should I attempt to do this? I'm not going to do it. I'm going to break my laptop. In real time, you can get captions across the bottom of the screen in Zoom. That's an example of multimodal learning that spans text and audio, right? We want to do the comparable thing here where we can blend all of this information that we can collect off of a system, fuse that into a latent space as a sort of foundation model, and then embed and then decode so that we can embed these physics models, these digital twins, but inside the context of a foundation model. Okay, so I'll talk a bit more at the end if there's time about that stuff. The specific challenges for multimodality here is that, in a traditional setting, multimodality would be, so you got a bird, right? You can imagine a sentence that says a red-throated hummingbird is in flight. You imagine an image of the same thing. What your brain does is it synthesizes those pieces of information in a way that's more than the sum of their parts. In science, right, we have the same sort of things, right? We have these, we can do mechanical testing. We can extract stress strain curves. At the same time, we can have SEM, TEM, these kind of microscopy modalities that are very hard to associate in any way with a PDE. Right, so one challenge is what do you do with that multimodality? The other challenge is, how do you talk about causality, right? So really what material scientists want is they want a self-driving lab, and robots are going to identify like some new unknown material that functions totally differently. So they want something causal that's different from how statisticians talk about causality. In that case, you want to say smoking causes cancer. We are absolutely positive of that. What material scientists are talking about is much more a plausible kind of pathway of upstream cause and effect relationships that can be used for hypothesis generation. So it gets a little bit philosophical, right? But it's less strict. It's more about organizing all of these modalities in a way that a subject matter specialist can wrestle with it. And there's a lot of exciting stuff for automation and robotics about, how do you tie that into campaigns to, explore this design space and so on. Okay, so the first thing I'm going to talk about is how we build these digital twins, and this is maybe going to be the most mathy part of my talk. So at a high level, I'm going to start with some cartoons, so that way I don't lose anybody when I get into the equations. But the first thing you need to do if you're going to talk about conservation structure is you need a way to talk about geometries, okay? So what I have over here is a unit interval, and I have these two red functions that partition it into two parts of the domain. And as I stiffen them up, you recover what you might be used to thinking about in a finite volume method, right? This would be like a disjoint partition of the domain. What we need to do in order to talk about conservation is we need to talk about the fluxes that are exchanged in between subdomains. So that's what this blue line is. And these are going to be examples of Whitney forms. These are smooth and differentiable generalizations of, cells and faces, but also for edges and nodes and so on, right? So what it means is we have something that you can throw automatic differentiation at, and you can machine learn a mesh. It's kind of the big idea. And at the end of the day, we have these formulas for these objects. And in order to construct them, if we can, this first one in the red is this zero form. This is the thing that defines a cell. If we can have a neural network that prescribes this function, the magical thing about Whitney forms is that the boundary is defined just in terms of these kind of differential operators, right, which you can push through auto diff. All right, so that's the first ingredient, and that's how we're going to talk about geometry and topology and how things are connected together. The second piece is we have to learn physics. So in this case, this cartoon is of potential flow past a cylinder. And what we're going to do is we're going to solve for these control volumes that I just showed you, but we're going to constrain them. And we're going to constrain them so that the sum of the fluxes is equal to the sources, right? Exactly what you would do in an undergraduate engineering course. Before you learn PDEs, it's maybe more fundamental than a PDE description of physics. And so what you can see here is that we're asking for a model that matches a true solution. And it's doing that. The dashed lines start to match the solid ones. But you see these In the background, this sort of polygonal, these round domains evolving around. So what they're doing is they're finding the configuration such that for each facet, the flux is a function of the state on either side. And if you looked at it, the sum of the fluxes would be to machine precision exactly equal to 0. Okay, so this is a very, very different picture. This is not physics-informed machine learning where you're doing physics by penalty. This is equality constrained learning where we're actually finding this description of physics that is completely unsupervised. So we don't tell it that there's a cylinder there, right? It found the cylinder because that's where the geometry should be so that you get a good physical model. Okay, so now in order to build up this geometry, there's going to be a few mathematical definitions we need. One thing is a partition of unity. That's a set of positive functions that take a coordinate as an input, and they output a scalar value. And it's a set of functions where each function is pointwise positive, and if you sum over all of them for a given coordinate, it's equal to 1. So we're used to this in a traditional scientific computing setting. This would be like indicator functions on a mesh, right? These would be like disjoint cells. Okay, but from computer vision, we're used to working all the time with classifiers, right? Where we would take a softmax of a neural network. That's a way to parameterize a categorical random distribution, right? Which is something that has nothing to do with geometry. It's a probability thing, but it has the same properties. Okay, and so that's the idea. So now this is our way to tap into a differentiable partition of space. You just have to accept that it's going to be smooth. That's the price that you pay, right? It's not disjoint. Okay, now the second ingredient that we need to prescribe physics is the generalized Stokes theorem. So you're probably used to from vector calc, right? The fundamental theorem of calculus, Green's theorem, the Gauss divergence theorem. All of these talk about the relationship between differential operators integrated over a mesh domain, whether it's an edge, a face, or a cell, and functional relation, differential forms evaluated on the boundaries of that object. So the generalized Stokes theorem writes this in the abstract. It's like one ring to rule them all, right? And it just says that if you know the boundary of a domain, then that defines a differential operator. And all of conservation structure, this is like the natural language of conservation laws, right? It says that between two subdomains, they exchange fluxes or circulations or whatever, depending on the dimension of the geometric object you're talking about, but they're equal and opposite. So when you sum over everything, they cancel out and you get a telescoping series. Okay, so we need to design schemes that will learn physics that respect that if we want to learn a model which will have that property, right? That conserves mass, momentum, energy, or whatever else. So this is all the ingredients all stitched together. What we'll end up doing is this is in the language of exterior calculus, right? But what this says is that in the simplest case, the divergence of the fluxes is equal to the sources. Okay, so we don't need machine learn that. We know conservation laws. We know what that means. Then the real machine learning, we only inject it in right where we don't know what's going on. Right, and that's how you define these fluxes. Like in general, those are typically empirical relationships, maybe Fick's law, maybe in some cases people tie it down to stat-mech or something. But oftentimes this is where people just make stuff up, right? And so what we're going to do here is we're going to have a black box neural network that relates the state on either side of a face to the flux itself, and then we'll stabilize it with a diffusion operator. Right? Usually when you design a scheme to simulate a PDE, each PDE has its own way of guaranteeing that it's stable. This is like numerical viscosity. We have no idea what kind of physics this thing is going to pick up. So we have to do something that can stabilize it and guarantee that we reverse engineer a solvable model. Okay, so that's how we get these sort of guarantees, is by introducing this artificial viscosity. And that's how all this stuff works. There's a lot of very deep connections to algebraic geometry that I'm probably going to gloss over here. But if folks are interested in that, I'm happy to talk about offline. Okay, so now let's talk about what is the actual mathematical definition of these things. This thing up at the top is the definition of a Whitney form. So this lambda, this would be that partition of unity function. Typically what's done in finite elements is you would pick like the top hat functions, the nodal Lagrange interpolants, the piecewise linear polynomial things that interpolate values on the nodes, okay? This formula, you can read these D's as a gradient. If this makes it more familiar, these carets are like a cross product. This formula, when you evaluate it for different K, generates different families, right? So this first family, like I said, it's the P1 elements that interpolates nodes. The next family, it's called Nedelec or edge elements. this interpolates circulations, right? The k equals 2, you pick up the Ravier-Thomas finite elements or phase elements. That's a set of shape functions which interpolate phase fluxes. This looks a lot like finite volumes if you don't have a finite element background. So the point of these things is that they're just a unique set of shape functions that interpolate corresponding differential K forms, right? And so now we have different function spaces to describe different laws that may naturally describe fluxes or naturally describe circulations, right? Think about like a circulation theorem for vorticity versus a conservation law, right? That would be something that would live here versus there. Okay, what's really special about this is now we can exactly represent a conservation statement. Okay, so if you have, say you have a scalar, you want to take a gradient of it, right? So this scalar field, you represent it in terms of degrees of freedom that sit on nodes. You take a gradient of it, you can represent the gradient of that field in terms of the fundamental theorem of calculus, right? So we can just say, okay, for any edge, the gradient of that field is the difference between the two nodes. That's the exact degrees of freedom on the thing one edge up. Okay, so in this way, there's no Taylor series, there's no approximation. Everything is exactly preserved. And that's sort of in a hand-wavy way, the picture about what's special about this. This is my last mathy slide, so if this is making you freak out, don't worry. What happens when you discretize, something like divergence of fluxes is equal to sources with finite elements? It gives you a discrete system, like a matrix, and that matrix is connected to what's called the graph exterior calculus, right? There's a graph div grad curl, and this is, people might be familiar with graph Laplacians, right? This is like the discrete version of all that vector calculus stuff that lives on a graph. Whew, it's hot. So what happens is that we get matrices at the core of this. We get matrices that correspond to the adjacency, right? These D operators is like a graph adjacency matrix. It says what control volume is connected to what other control volume. And the mass matrices in the finite element method, it's like a weight on these operators. Or if you come from a machine learning background, you can think of this as an attention mechanism, right? It tells you what control volume pays attention to what other control volume because they share a face and they share mass momentum, whatever, transfer. Okay, so there's a lot of structure because of this connection to graph. They call it cohomology or combinatorial homology. Like if you talk to math people, they have like all sorts of very confusing fancy words to talk about it. But at the end of the day, there's just matrices, right, that describe how everything's connected together. So when we've learned these Whitney forms, what we've learned is all of these matrices with a very special property, which is that the divergence of the curl is equal to 0, the curl of the gradient is equal to 0. That's exactly what you know from vector calculus, right? But once you get into discrete versions of vector calculus and get into electromagnetism, get into all this stuff, you need to actually get that exactly right. Okay, so you don't need to read these theorems. The important, like the so what of all of this, like why bother with all this complicated math? The point is that it gives you the building blocks that people use in traditional finite element methods. So if you took my class this semester, if you're not, you should take it. If you take an introductory course in finite elements, they would teach you this is how you discretize the Poisson problem. You prove that it's stable. You prove that it converges to a true thing. We can do all of these same proofs, right? Which if you've worked with pins, if you've worked with these other kind of machine learning frameworks for trying to get physics in, there is nothing that you can say about how stable or whether it's conservative or all these kind of things that are like bread and butter for standard simulation. Okay, so this is why it's worth cracking into a book and learning some math and whatever, but for now, just take my word for it. So like I said, the way we learn models, right? We have data, we reverse engineer a model that can predict, that matches the data. I already described this, we split it into a flux down here, a conservation statement up there. At the end of the day, we have a model that looks like a diffusion plus a nonlinear flux. This is where the black box physics lives. And we solve the equality constraint optimization problem. So in general, you can't do equality constraint optimization. Like who knows if you can enforce that constraint? Who knows for an arbitrary neural network whether you can solve this system? But we can prove that this has a unique solution as long that's what all those finite element building blocks gives us. We can say as long as this is diffuse enough, this will always have a unique solution, even if we don't know the functional form of that nonlinearity. Okay, so that's the idea behind Whitney forms. Now I'm just going to dive into all the stuff that we do with them in my group. Everyone's probably familiar with conditioning in some way, shape, or form. For example, in Dolly, you can give a text prompt and it'll generate an image. You can think about that as a way of sampling from the space of images conditioned on the text. Now imagine that you can sample from the space of finite element models sampled on an experimental measurement, right? And that you can do that in real time. So the output of this finite element model is going to be something that's the number of control volumes. So everything I showed you before, that was like 5 control volumes. So we're talking about it'll spit out a model that's like a 5x5 matrix that you have to solve. That's something that you can put on an Arduino and solve in real time. Okay, so that's the core of this. And now the conditioning is that you can make that adapt itself to whatever sensors you're picking up. Okay, so first, here's a picture of what the architecture looks like. This is something that my group's been working on maybe in the last year that Brooks has been leading. Right, so along the top, this is where we learned the Whitney forms. We learn these partitions of unity. This is where we do automatic differentiation in order to figure out the boundary operators and all that stuff. Now that spits out the mesh. Along the bottom, this is where we learn the fluxes, right? So we have like a branch trunk structure, if that's a meaningful statement to you. But now what we want to do is we want to condition that on extra information. This could be like a vector of temperature readings, or it could be another field variable. It could literally be anything at all, right? And what we're going to do is use cross-attention or even just a plain old MLP in order to modulate the model so that whatever that conditioning information is, it'll change the physics and it will change the geometry at the same time. Right? But we're solving the exact same system. It just has this like extra knob on it in terms of this Z variable. Okay, so there's some details about how to set that up. The important thing is that there's some nice linear algebra so that you can kind of build this in a non-invasive way on top of traditional finite element codes. That means you can handle complex geometry. It means like if you have an industry collaborator, they're not going to freak out because you say, oh, I've got to get like a team of software engineers and get into your code and do that for 2 years before we do anything. If they can spit out mass matrices for whatever their simulation setup is, right, we can just kind of put this on top as a layer. It's like a nice software engineering thing, but maybe not important for this talk. Okay, so here's a picture of how this works. I'm going to look first at just some simple 1D problems, some toy problems. This is an advection diffusion problem. The Peclet number describes the balance between advection and diffusion. And if it's advection dominated, this is very small. And you get, or Peclet number is large, the diffusion number term is small, and you get these very narrow boundary layers that are challenging. So in the first version, what we can do is we can say, okay, here's the solution to the advection diffusion problem. On the left, you can see it reverse engineering these partitions or these shape functions and the physics on them so that when they solve it, it gives you the exact same answer. Now what we can do is we can condition on the Peclet number, right? So there's a knob on our finite element space and on the physics, so we can dial in how much of one or the other, right? So think about this like we've extracted a family of finite element models that we can tune in. On the right, now what we're going to look at is, you can do this for nonlinear systems. It doesn't have to be 1D. On the right, what we're going to look at is a shock problem. A SOD shock is a standard thing in shock physics. And we're going to take a data set where we are solving for different material parameters, right? Where the data came from ideal gases, but with a different ideal gas constant. And so this is at training along the top. You can see over the course of training, it's working out what these partitions are. Now it's found them. Then it really locks in. Now it knows how to like get the physics on top of these things and so on, right? But when you solve this, now what we can do is we can dial in those different material properties, right? So we can do material calibration in real time is basically the punchline of all this stuff. And we're doing, this is some of the stuff that we do where we'll like coarse grain molecular dynamics into shock physics and so on. So that was a supervised version of a problem where we have an example of what should be going on. Right, we have labels, right? We know what the solution is. Now, and we know what the corresponding Peclet number is, okay? Now pretend we don't know what the Peclet number is. That's like hidden. It's some exogenous variable. It's like a hidden parameter that, maybe a scientist would know it's in the mix, but Do they know to like add that as an input to their model or not? So what we can do is we can hide the Peclet number. We basically just wedge all this machinery in the simplest case on a VAE. Right? We can do more sophisticated stuff. There's people in my group working on stable diffusion for this and other, flow matching, other fancier things. Right? But the idea is that you can do the standard thing. We can just use variational inference to solve for what that variable is. So what it does is it identifies the Peclet number, right? It never knew what it was. If we plot the latent variable and we color it by Peclet number, we see that it's identified a variable, which is the Peclet number. You know what I mean? So you can interrogate this with, kind of interpretable AI ideas and so on. And now you can identify what these missing physics are. Like I said, you can do this for complex geometries. The thing I'm going to take a deep dive now into is what would be relevant for the robotics side, and where the first big robotics project that I've been getting involved in is how can we use this for source identification? Okay, so on the right, this is just a toy problem. This is the Poisson problem with the point source, but the point source, now we're conditioning on where the point source is at. Right, so what you can see is it's finding partitions that follow, it's almost like it's punching it out, right? And you get the near field, and then you get the far field, and then you get the boundary, right? What's really important about this from a physics perspective is the flux out of this domain is to machine precision 1. It's exactly what's on the right-hand side in terms of the point charge. So we've used this stuff to build digital twins of maybe more standard systems. This is one project I'm working on with Professor Pertikaris and other folks, George Pappas at Penn, right, where we'll do these massive simulations. Right? In this case, we would take a computed tomography scan of a lithium-ion battery microstructure. We build finite elements for it. We train that. We extract one of these models that gives you like 8, it's like an 8x8 system that you solve instead of a 6 million by 6 million system. Okay, so it's much, much faster. Then also at the same time, we're looking at battery packs, right? So this is like a server room, and one of these batteries right in the middle is super hot. And you need to cool it in a way that reflects that something's happening at the microstructural level, right? So basically, this is an example of the systems of systems stuff where it's like, yeah, we can make 2 of these surrogates, we can hook them together, the conservation stuff is preserved, and you get the right thermodynamic budgets, right? Exactly what you would do in undergrad engineering. Right, so this is the main stuff that I did before I came to Penn, and we keep working on it. The stuff that I'm excited to talk about today is the stuff I've been working on with Ben and Ani Shia, where we're looking at the source identification problem. So one example of that would be the Deepwater Horizon. Maybe I'm getting old. This is like when I went to grad school, this happened. So basically, there's an oil spill somewhere at the seabed. How do you figure out where that event occurred? It's like a point process. It happened somewhere. And how do you locate it so that way, as fast as possible, you can mitigate and come up with a response? Right. So in environmental stuff like oil spills, that would be a good example. National security contexts. You could imagine, like, God forbid, somebody set off a chemical weapon in downtown Philly. How do we know where to send a bomb squad to? How do we identify, just based off of the fact that we can see some tracer species leaking out? Now, how do we reverse engineer where the source is at? Okay, so mathematically in robotics, the way people approach this is with the optimal coverage problem. And so if you assume that there's a probability distribution on the spatial coordinate, so what's the probability that this random event happened at a single coordinate? This problem says, what is the optimal configuration that I can put my sensors so that I maximize the odds of detecting that event? Okay, and basically the idea of the algorithm, the way it works is you take all your sensors, you build a Voronoi diagram, you come up with this probability distribution, you compute the centroids of each one of these polygons weighted by that probability distribution. That gives you a centroid, and then you tell the robots to chase the centroid. Okay, so in this case, imagine like a big Gaussian over here. This black dot is the event. These are all going to chase this, they're going to chase the centroid of the polygon that's weighted by this Gaussian, and that steers them over here. Now, at the end of the day, you've got good coverage around that event. Typically, these probabilities are defined empirically or ad hoc. I've just got a good feeling, or there's like a feature there or whatever. What we want to do that people aren't doing is make this physics-based. How do you do physics-based optimal coverage? So what we do, here's a toy example that Ben's been working on, right? We can take that last example that I already showed. And now what we're going to do, we're going to have a learnable source location, but it's going to be conditioned on each one of the sensors being these white dots. Each one of the sensors can measure this, this potential field value. Okay, so what it does is on the fly, every time the sensors move, it updates in real time and it gets a new model they can use to solve it. So you can see it here. It's not perfect. You have to accept that these models are gonna, like, each one's solving like a 3x3 system, right? This is not gonna be a high fidelity finite element solve, but it's enough for them to chase these sources around. So this is a static source. This is a moving source. And you can see that this is enough for them to follow it and then get the error down around, like, into the engineering eyeball norm for these surrogate models, right? So this is like the inverse part of the digital twin. What we've been working with is Spencer Folk, who's working in Vijay Kumar's group, did this great work where they built up this database of an urban environment and just doing kind of 2D Euler equation flow through it. And they were using that to build these on-the-fly pictures where, based off of LiDAR, they could predict a local flow field. And so they were interested in doing that as a way to do optimal path planning, right? That you can say, oh, it's very turbulent over there. There's gonna be a lot of drag. Don't go there. Go around this way, where it's easier to fly through. And they're interested in minimizing like fuel usage and stuff like that. What we've done with this database is this is ongoing work, but that Ben has overlaid this with an advection diffusion solver. So now we can generate a data set by just randomly plunking down different point sources throughout the city. We can see where do they get advected to. And you can see over here, this is what it looks like, that we're conditioning on different point source locations. And this is what the extracted physics model would say the corresponding flow field would look like. Okay. On the top, you can see the solution to these problems. It has a singularity, right? So we're less interested in getting the peak right. We're more interested in getting the far field structure right. And you can see that the error is concentrated at the peak. It doesn't do a good job resolving the singularity, but it's crushing the far field, right? And that's the thing that you would want to chase in order, if you want these agents to follow the descent upstream to where the source is. Okay, so we're very encouraged by this. This is sort of early days. The last thing about the digital twin stuff I want to talk about is the uncertainty quantification. So in standard finite elements or forward simulation, whatever your discretization method is, the backbone of engineering for these methods is called verification and validation. It's how do you know that the simulation isn't just a pretty picture? And the backbone of that is grid refinement. So you have mathematical theory that guarantees as you increase your resolution, if you can prove stability for your method, that implies you are guaranteed to recover the true solution, right? So it's not just like somebody showing you an ink blot test and you see what you want to see, right? You know that it agrees with the physics. What that means is that people will refine a mesh 2 or 3 or 4 times. If it gives the same answer, you're good to go. You don't have to think that hard about it once you have this guarantee. You don't have that for machine learning. You go to a bigger neural network, it's not going to give you a better answer. Oftentimes it gives you a worse answer. Nobody has any idea what they're doing with convergence with neural networks. It's like a big, unspoken, ugly truth. Okay, so what we need is the equivalent thing, right? How do you know that you can trust these models? How do you know where they're wrong? We've been doing a lot of work with this for semiconductor physics. Like if you have a chip on a circuit board in space that got hit with radiation, inverse problems in the subsurface, you might have a bunch of wells where there's fracture networks going underneath, but you have no idea what's going on in between. We're also doing some work with Alison Marston's group on cardiovascular networks, right? So this is a framework that's going to map across like tons of different applications. It's really about how do you take these Whitney form models and how do you plumb them with uncertainty quantification. So the idea is we want to take Gaussian processes, which I'm assuming everybody, Penn's fantastic, so everybody knows what a Gaussian process is. Gaussian processes are awesome because they have this analytic expression for the posterior. That means you get these sausage plots that say when you're close to the data, the uncertainty is low. When you're in between, it's high. If you're extrapolating, it's super high. And you don't have to do any sampling or complicated schemes to do that. It's just linear algebra in order to get it. The challenge with that is that you can't do it for very big data. So it's great for like 1D problems and so on. And there's tons of Bayesian optimization you can do built on top of this, right? But you can't really apply it to like PDE scale systems. So the thing my group's been working on with Humano Hadi's group at Caltech is this idea called the optimal recovery problem. And it's just a completely identical way to do to construct Gaussian processes. But instead of doing it with linear algebra, you solve an optimization problem. So the way to read this is you solve a problem that says, give me the kernel reconstruction that's as smooth as possible that also interpolates the data. And there's like a little penalty parameter here. That gives you a quadratic program to solve. And when you solve it, lo and behold, it gives you the exact same thing that you would get from the standard way. So oftentimes this is taught as like a mathematical curiosity in kernel methods classes in machine learning. The thing that we can do here is once this optimization problem, now you can throw equality constraints on it. So what we do for each one of these fluxes, instead of treating it as a black box neural network, now each face of our domain gets a Gaussian process. And each one of these Gaussian processes, right, this is a sum over all the edges of this graph. Each one of these Gaussian processes are coupled together through the constraint that the sum of the fluxes equals the sources. Right, so what we get, this is a toy example, just like a resistor network in series. What you get is each one of these has an uncertainty prediction on it. Right, so you get some error bars. Why is that important? Here's an example where we were fitting a model to a semiconductor. We got a big like PDE simulation, and then we fit one of these lightweight models to it. If you look, we get a great reconstruction, right? You could see this. You could go to your boss, who could be like, grad students do this all the time. They say, oh, the error is low. Like, what does it mean that the error is low, right? Like, the first thing that people say is the error is under 1%, and that's like the engineering norm or something like that. So you'd be tempted to take this and then use it to design a circuit. When you plot this on a logged scale, right, this is the exact same plot of current versus the voltage drop over the device. When you plot it on a log scale, what you see is like, you're attempting to regress something that spans over 12 orders of magnitude, and it breaks down at a certain point. So you could be fooled to think that this is the range of applicability, but now because we have this error estimate, you say, if you use this anywhere for a voltage drop above -1, you're in trouble, right? It's going to be completely wrong. Okay, so you can do this in other settings, like we use this for inverse problems for the subsurface flow stuff. Say you have like measurements of flow and pressure at the surface bore of a well, but you have no idea what's going on because like the fractures the flow is propagating through is like miles underground. You can't actually measure that. So in this case, we can make predictions, same as before, but now what we can do is we can say, what is the uncertainty? If you want to ask, what's the flux coming out of one of these wells or whatever else, right? Here's another picture. And you can see, right, the effect of the fact that you're trying to solve a ill-posed inverse problem. Okay, the last piece I want to go through is something that may be more, we've been interested in this from a molecular dynamics or maybe chemistry picture, but I think this is something for robotics that could have be very useful. And that is looking at irreversible processes and how do you do machine learning for dynamics. So everything I talked about so far, it's like conservation laws and divergences and all that kind of stuff. There's a different kind of geometric dynamics, which is about conservation of area and phase space and all the kind of things that probably this crowd, you probably know it better than I do. So within this space, if you want to learn dynamics, meaning x dot is equal to neural network of x, that would be a neural ODE. That is the most black box. You're assuming nothing about a model. On the other end here, you have the strongest physical priors, right? You actually assume you have a dictionary, or maybe there's like 20 candidate kinds of physics that could describe a system, but you know how to build that dictionary. Halfway in between, people have been working maybe the last 5 years now on structure preserving neural networks, which assume that the dynamics are reversible. You don't need to know what the actual functional form is, right? But you can guarantee that it will preserve an energy. So there's a lot of interest in this, both in physics, also just, the other way around, like science for AI, that you can construct neural networks that aren't allowed to explode because they conserve an energy, right? That would violate energy conservation. So different people are interested in this in different ways. The problem is you can't handle dissipation, right? In real life, we have dissipation. So what we've been looking at is this extension of Hamiltonian mechanics. So if you ignore this M grad S, this looks like a non-canonical Hamiltonian system. And like a Hamiltonian system, this energy E, it's invariant. It stays constant over the course of your prediction. But the second piece in metroplectic dynamics is now you have this entropy. And so you have a skew symmetric matrix L, you have a symmetric positive definite matrix M, and also this very tricky to deal with degeneracy condition that I'll talk a little bit more about. But the important point is that this is all you need to prove that you get a conserved energy and a non-decreasing entropy. So historically, the way people have looked at these models is they derive a model and they say, oh crap, this is a metroplectic system. That means I get all this theory for free. Right, what we're trying to do is reverse engineer a neural network that will fit dynamics of this form to data, right? You give it time series, we'll spit out a model that's guaranteed to have this. This is what these proofs look like if you're interested in that. I'm not even going to attempt to get into any of the details of it other than just to say we have this big neural network. We have a few different papers that we've written on this about different ways to fit for graph data, how to fit these kind of dynamics to a given system. There's a lot of interesting connections between graph attention and so on. I'm not going to bother with that. The thing I want to talk about is what happens when you look at coarse-grained systems. So this is a classical system that people look at. This is Brownian motion, like what Einstein looked at under a slide with pollen. Right? So if you have each red dot, think of it as a pollen particle. At a microscopic level, it's getting bombarded with water molecules. And it's like ping pong, right? If within a given instant, it gets hit more from the left by water, and it just happened to not get hit by the right, then it'll push it by momentum transfer to the right. If you throw away all of the water molecules and you just observe the pollen, it looks like a random walk, right? And this is what we mean when we say coarse graining. It means that we're going to take degrees of freedom in the system, throw them away for this much smaller and easier to simulate or maybe to observe experimentally system. They're going to try to find a different system of equation that accounts for the fact that we made this way over optimistic hope that we could just pretend water doesn't exist. So what happens when you do that, even if you start with reversible dynamics, just from entropy, you're losing degrees of freedom. You're losing information. That means you have to be able to catch this kind of dissipation. Also, at the same time, if your system has become dissipative, but it's a reversible system, you're going to violate the first law of thermo, right? Because you're just going to lose energy that shouldn't be lost. So you also get work that has to be done by the system in terms of thermal fluctuations. And what you need to preserve for all of this is something called exact fluctuation dissipation balance. This work has to exactly equal the dissipation in order to get the non-equilibrium statistics right and all this kind of stuff. So we've been working with a collaborator at Carnegie Mellon who does very large-scale star polymer simulations. So a star polymer, it's like a polymer, looks a lot like an octopus, like a lot of tendrils branching out and joined at a single point. What we want to do is remove each one of these very expensive. You don't want to simulate every single atom and every single tendril. There's like 200 atoms per one of these things. What we want to do is machine learn a single atom that has the exact same equivalent dynamics. And so if you throw that through a graph neural network, right, it won't preserve any of this non-equilibrium statistical structure. Right, but we do get that. This is work that Kirkus has been working on in my group. This is in lamps. We can do this for like billions of particles just because it's in lamps. You get that for free. So from the robotics side, I was super jazzed up because Rebecca, forgetting her last name, Battaglio, right? Was visiting yesterday, and she was talking about active agent-based robotics where you could imagine that you have a smart material that has an actuator on it that will, you press a button and it'll become compliant. You press another button, now it gets very stiff, and you can control stuff at this sort of level, right? So I think there's a lot of tools here that could be really exciting to try to look at, that type of a agent-based control system, or it doesn't even have to be a physical system, right? People look at this for like flocking dynamics. People look at this for, traffic, like whatever. There's a lot of places you could take this theory. Well, so part of what I was hoping to achieve by coming here was to seek out collaborators and data sets and stuff like that. I've been working on this one project with Paulo Aradia in MEME. So he's like a dense suspension flow guy. What we've been trying to build toward is this idea that really sits halfway in between computer vision and data-driven models, that you don't do any simulation at all, right? You just get your data from raw experimental data. So he has these videos. It's like a 2D colloidal suspension that he's sharing back and forth. And he takes these videos and he's doing computer vision to get per particle trajectories of exactly where they're going to go. Right, so a big challenge with all the machine learning for science stuff is it's all built on synthetic data that's very, very expensive to curate, and it's hard to get at scale. Whereas you can do this. So I want to share this also as a direction that my group's going, in case this is something people are interested in, right? Like the bridge between taking computer vision data and then fitting physics to it. The last thing I was going to talk about that I'm going to skip, I'm just going to flip through really quickly, is how we were using this stuff in order to do scientific discovery. The idea that you can use automation, it doesn't have to be fancy robots. It could just be like clever staging with microscopy slides and stuff like what's shown here, where we would take these printed materials and we would try to like explore the space. I mentioned that already. The architecture that we've been looking into for this for a while, it's kind of like, it's like 5 years old at this point, which means it's like the Stone Age of machine learning years, is we took all this multimodal data, we pushed it through encoders, we did a product of experts modal fusion into a latent space where we can impose a Gaussian mixture prior. So that means that we're fusing all of these into a way that it identifies them into clusters in the latent space. And then we decode, some of the modalities like images, you decode them, what can you do with microscopy? But the physical modalities, we can push through one of those Whitney form models that we talked before. Like these models are lightweight enough, you can embed it in a neural network. You can train this whole mess end to end. So you can say, what is the set of clusters in my data set that admits a good physical model, right? So you can solve for that. So I just wanted to show this one data set. So this is a bunch of 3D printed lattices, uniaxially compressed. We get stress strain curves. We also get images. And so when we train a model like this, basically in the latent space, it's trading these images back and forth, trying to disentangle the data set. In this case, we have two different kinds of lattices. And you can see it trying to fit a physics model to the right. This is a linear strain hardening model. But then on the left, the image modalities, it's identifying that the ones that look like this have that physical response. The ones that look like this have that physical response. Right, so this is a toy problem. It's not super exciting, right? But now you can imagine that you have like 20 different modalities, and how can a human being like identify which patterns are physically relevant or whatever? And even this toy problem, we just put out a paper this year about how this highlights the exact failure modes. So it turns out one of these lattices turned to be like very poorly performing. Like sometimes it was good, sometimes it was bad, but it was totally unreliable. And so these clusters revealed that there's like a geometric fault inside these things. So it's more just to get your noodle going about, you can use these things to do forward simulation. You can use them to do control. You can also embed these in other systems just for trying to understand scientific data and so on. So maybe I'll stop there and have a few minutes left to take some questions.
So we've got time for questions. I've got a bunch. Anything online? Okay, so just from a robotics point of view, it seems like that's the swarm. I mean, the you had the coverage problem, which is like swarm robots, and then also the thing with the potentially variable stiffness array of that kind of thing. Seems like a lot of these things those types of things involve lots and lots of agents, and things get more interesting when there are more agents. Is that generally true, or is it like if you only had 3 or 4, does it still make sense to use these approaches? Or
it still makes total sense, right? There's still structure, but like imagine you just have like a single arm, like making Ford F-150s on the assembly line. Over time, you want a digital twin of that because the nominal design of the robot was, there may be some crude accounting for friction and wear and tear and stuff like that, but it just depends on the use. Every single agent in that fleet will have a different wear pattern, and how do you wrap your head around that, right? So even in that case, right, which is just, and this is most of where the research is right now, and why people are like, they're not stressed out that they can only handle 5 degrees of freedom, right? Is that's enough to do a real-time updating of that type of object, right? For us, it's because we've been doing these like huge particle simulations, so that's why our tool set was already aligned there. But across the whole community, all over the place, it's not that swarms are particular in any way.
Thanks. More questions? No question online.
I can read.
Read it.
I got it up here. So Nadia is asking or saying, great talk. You often mention real time. What does real time mean to you? Is it that you're able to make predictions in minutes, seconds, milliseconds, microseconds? Which is a great question, that every system has a time constant associated with it. And it's very difficult to make a blanket statement. The main thing is like at the crux of all of these, after you do the conditioning, and we've been talking about how you can do that offline, right, in kind of like a server client configuration. But after you do the conditioning, in order to solve this model, you solve a 5x5 or a 10x10 or whatever linear system. Maybe a nonlinear problem, so you might have to do a few iterations with a nonlinear solver, but you're still talking about something that's like sub-second. So the stuff that we do with people that do fusion power, that's like unbelievably slow, and they would laugh at you, if you said that was real time. For climate stuff, that's very fast. So it's difficult to make broad statements, right? But at the core of it, that's the time scale of evaluation for these models, right? The time that it takes to solve like an order 10 system with a dense linear solver.
Thanks, and thanks, Nadia. Other questions? Okay, maybe I'll have one more. So maybe, so just a kind of maybe a dumb question. I don't really know that much about reinforcement learning and machine learning and that kind of stuff, but I did have some exposure. And one of the things that currently with reinforcement learning is a big problem is sim to real. And it seems like from what you're saying, the digital twins and the physics-based guarantees could help with the sim to real problem. Is that basically what you're doing, or is it something that could be applied?
So people, but make sure you're speaking the same language. So when people say sim to real, oftentimes it's that you're training on a simulated data set, but then you want to do inference, you want to execute the policy on a different system. So machine learning, they might call that distributional shift, right? Like your training set doesn't match your inference set and so on. You would hope that this is useful. The other thing is like we can train this on, that's why I personally am trying to move toward experimental data altogether to get away from any kind of unrealistic simulated assumptions. So there's that. But then the reality is that even if you have unrealistic simulated data, this will solve for the closest physical model. Think about like a projection, right? It gives the closest model that matches your data, but it still obeys conservation principles, right? So it could close that gap, but we haven't done any of those kind of comparisons specifically, but it makes sense, yeah.
Okay, let's thanks to speak one more time.
Thanks, Mark.